poll reported that 66% of adults were satisfied with the job the major airlines were doing. Suppose 20 adults were selected at random, and the number who are satisfied is recorded. And then we have 5 parts to deal with here. Okay, why is this a binomial experiment? First off, we have a fixed number of trials asking the question of 20 adults. And since this was at random, then I would expect, number one, that their responses would be independent of how others are responding, and that we should have, from those 20, something pretty much reflecting what we see more broadly with that 66%. If we consider success, that they are satisfied with the job major airlines are doing, then little p is 0.66, staying fixed from trial to trial. And finally, there are just 2 outcomes. Either they're going to say that they are satisfied or they are not satisfied. Two mutually exclusive outcomes, satisfied or not satisfied. Fixed number of trials, 20. Independence due to the randomness. And the probability of success is the same in each trial. P equals 0.66. Find and interpret the probability that exactly 11 of them. Okay, that's 11 out of the 20. So let's use the formula I just showed. Well, not the formula that I showed in the previous video, but instead the calculator shortcut, because I only showed it for one on that. Okay, so that's for a single value of X, single point. Now we've got 20 trials. Probability of success is 0.66, and we want exactly 11 of them. And that's supposed to be the 4 decimal places, i.e. the 10,000ths. That will round up to 0.1056. So if we were to do this over and over and over again, 20 adults in each simple random sample, do this 100 times, then I would expect the average to be close to 100 times 0.1056, which would be 10.56. That is going to round to 11. Okay, so there were the number of adults that were satisfied in each of them. We'd see that in about 11 of the 100 surveys. Compute and interpret the probability that at least 16 of them. Now, I believe that that is referring to that single instance of a simple random sample of 20. We could either do the following. Looking back at this original formula, but then at least 16, we're going to go up to 20. And you could not have one of those simple random samples of 20 of them where you get different results as to how many are satisfied. So these are mutually exclusive. I don't want to write all of these, so I'm going to put a dot, dot, dot. So one of my options would be to use the formula at the top with n equaling 20 and little p equaling 0.66 and add all these up. Okay, I'm going to go through that, but then I'm going to show you another option. So let's see here. All right. So we have 20 C16 times that probability of success being 0.66 raised to the 16th power. Probability of failure, 1 minus 0.6 is 0.34. And there would be 20 minus 16 or 4 of them that are not satisfied. And then I'm going to add to that 20C17 times still 0.66, but now it's to the 17th power. It's going to leave 3 that are not satisfied. Add to that 20C18 times the 0.66 raised to the 18th power times 0.34. That leaves 2 that are unsatisfied. 2 more to go. This approach is not fun with this many things to add. 20C19 so probability of satisfied was 0.66. 19 of them are satisfied. Notice how I keep scrolling that to the left to get out of the exponent before I type more. Only 1 is unsatisfied. And finally, 20C20, that is 1, by the way, so I'm not going to type that. 0.66 to the 20. 0 are dissatisfied. 0.34 to the 0 is 1. So if I didn't get lost in all that typing, then if they want this to 4 places, this should be 0.1374. Let's find out. Yes. Remember, 4 places after the decimal point is the 10,000ths place. There we go. However, there's another option. I'd shown that there were 2 things about binomials. CDF goes from 0 to something. So if we want greater than or equal to 16, but binomial CDF goes from 0 to something, we could say that this event here is the complement of x being less than 16, which is the same as x less than or equal to 15. And since we're dealing with x less than or equal to 15 being the complement of this, we'll have to subtract 1 minus. So let's get that in there all at once. By the way, it'd be a very good idea to show what you are typing into the calculator, not just the results. So CDF, cumulative distribution function, everything from 0 up to the last x value of 15. And let's see if we get 0.1374 after rounding again. And we do. All right. Interpreting this. So if, again, we're to do the simple random samples of 20 adults, but we do that 100 times, 16 or more would be expected to be satisfied in about how many of the surveys? Multiply the 0.1374 by 100, 13.74, round that up because you're not going to have a portion of a survey. So about 14 of the surveys. Between 8 and 12. Now there'd actually be less to add than previously. At least I think so. Let's see, that was between 9 and 12 of them. Inclusive, so or equal to. There would have been only 4 things to add instead of 5 things to add. But what I'm going to do is this. If I do the binomial PDF up to 12 and subtract something to do with this, let's see, we want to include the 9, so I need to leave out from 0 to 8. Let me clarify why that is. So remember, we had 20 trials being performed. I don't want to write all of these, but we're being asked for the probability of 9 to 12 inclusive. We want what's in between here, including 9 and 12. If I were to put in the binomial CDF up to 12, that's going to include all of this as well. So I need to cut this part off. This would be the probability x is less than or equal to 12 minus the probability of x less than or equal to 8. So putting that into binomial CDF. All right, let's do this. It's going up to 12 and subtract from that. CDF going up to 8. To 4 decimal places, that would be 0.4371. Let's see if they do want it to 4. Yes. All right. And if we multiply that by 100, we'd get 34.71, which would have to round up to 35 of these surveys where we'd have between 9 and 12. And our last question. I'm going to make a mistake here because I want you to see something. Actually, let me check something. One moment. I think I'll take that back. There is a certain situation where determining unusual events by calculating the probabilities the usual way we've been showing in this section does not apply because, well, with large enough n, depending on the value of p, it may be that every individual event, every individual outcome, i.e. every individual value of x, might be leading to very small results. And though here we would have more than 17, meaning x is 18, 19, or 20, that sum still might be very small. It's dependent on the value of n and p. There'll be more about this in the next chapter, but if we check whether this is greater than or equal to 10, we may want to check for unusual events by comparing to the normal distribution and the empirical rule. But in this case, we've got n is 20 and p is 0.66. 1 minus p is 0.34. And I don't think that comes out to be greater than or equal to 10. It does not. It's not greater than or equal to 10. And so what I was thinking might apply does not. Instead, we're just going to compute this the usual way. Again, adding 18, 19, and 20 using this formula. When R is 18, 19, or 20 may not be so bad with only 3 to add, but that would be 3 applications of that formula. However, more than 17, i.e. greater than or equal to 18, then I'm going to use the binomial CDF. If we want to leave out 18, 19, and 20, this will give us everything from 0 to 17. And this event is the complementary event of this one. So we need to subtract from 1. All right, so let's see here. We did something similar previously. So let's see. If they want that to 4 places, that would be 0.0152, which is less than 0.05. 0.0152. Double checking that. Yes. And so we multiply this by 100 and round appropriately. We'd expect more than 17 satisfied in about 2 of the samples. All right.